Hey everybody, so we're talking about gas laws now, and I want to bridge the concepts of stoichiometry over to some of the gas properties that we've been talking about. And so I thought the problem that you see here would be a good way to show the connections between both. So let's first start by looking at a process and working through this problem together. So the question asks us to find a volume of hydrogen gas at STP. Now when we see STP, that might initially be something new to us, but all it really means is at standard temperature and pressure. And for us, standard temperature is 0 degrees Celsius for a gas, and standard pressure is 1 atmosphere. So when it says standard temperature and pressure, that just means 0 degrees Celsius and 1 atmosphere. And the reason why that matters is because there's certain things that are true about a gas at standard temperature and pressure, at least for an ideal gas. And remember that we're treating gases that we come in contact with in normal lab conditions as ideal gases. What we can say at STP is that 1 mole of any gas, doesn't matter which one, occupies the same volume, 22.4 liters. So whether we have a mole of hydrogen gas or a mole of water vapor, it doesn't matter. 1 mole would still take up the same volume. So fundamentally, these types of stoichiometry problems are nothing more than traditional stoic problems, just with an additional conversion between volume and moles, something that Avogadro's law would allow us to easily think through if we were to look at it through that lens. But anyhow, let's take a look at this problem and solve it. So we're essentially reacting zinc with sulfuric acid. Anytime you're doing a problem like this, start by writing a balanced equation. So we've got zinc metal and sulfuric acid, H2SO4. They react together in a single replacement reaction. Remember that zinc is more active than hydrogen in the acid, so it can kick it out. We get hydrogen gas kicked out and zinc sulfate. We do a quick check to make sure it's balanced, and it's balanced already. We'll add some state symbols in here just for clarity. And you could use your solubility rules to predict that zinc sulfate would be soluble. But anyhow, what we're really concerned with here is not the zinc sulfate, we're concerned with the hydrogen gas. So that's what we're going to pay attention to the most. So you notice we started with a given amount of zinc. We've got 16.35 grams of zinc. And if you remember, the ratios of a balanced chemical equation aren't really useful to us in terms of grams to grams. Those proportions don't hold up because of the different masses of the elements and the elements and their compounds that they form. So we have to convert into something more useful, into moles. So the first thing I'm going to do here is convert grams of zinc into moles of zinc, something that's a pretty constant algorithm that we've done throughout the course. So we take 16.35 grams of zinc. We refer to our periodic table, the molar mass of zinc, 65.39 grams for 1 mole of zinc, and we get an answer of 0.25 moles of zinc. And now from here, there's not a lot of stoic left to do because the equation balanced out and everything is in a 1-to-1 ratio. So what that means is if we have 0.25 moles of zinc, we're going to have 0.25 moles of hydrogen because there's a 1 mole of zinc to 1 mole of hydrogen ratio. And remember, those coefficients in front of the balanced equation are what give us this mole ratio. And also remember that even when there's no numbers there, there's an implied 1 in front of every single compound or element in an equation. So we get our answer here of 0.25 moles of hydrogen gas. Now's where the problem diverts from a traditional stoichiometry problem. And this is where we have to remember, hey, there's a reason why they told us STP conditions, and that's where we're going to use standard molar volume. So to actually figure out the volume of hydrogen gas, we just have to do one final conversion step, converting from moles of hydrogen into volume in liters using the molar volume equivalent. You could also use Avogadro's law, you get the same answer. You could even use the ideal gas law. You'd still get the exact same answer. It makes no difference how you do it. You're going to get the same answer here. So here we go. 0.25 moles of hydrogen gas, and the ratio is 1 mole of any gas, 22.4 liters, and you multiply that through and you get essentially a quarter of 22.4 as your answer. And if we look, we should give our answer to 4 significant figures. So in the end, we end up with an answer of 5.600 liters of hydrogen gas. So fundamentally, in all of these problems, you're going to just have to convert from moles into volume, or you could, on the flip side, convert from volume into moles. Hope you found this helpful. Have a great evening.